Can you see my slides?
Yes, I can.
Okay. And I'd like to thank Professor Yuan Xiao for inviting me, for giving me this opportunity to talk about my recent work on application of tensor networks in several fields. Here I draw several figures. On the left, there is a statistical mechanics problems, and in the middle there is a machine learning problem, and on the right hand side there is a quantum computer simulation problem. So we basically tried to use tensor networks as a unified framework to deal with different problems in different fields. So my background is actually the statistical mechanics problem. So it's easy to introduce actually. So consider a vector composed of n binary components, each of which takes two values, positive 1 or negative 1. By positive 1, there's a up arrow, and for negative 1 is the blue arrow. And in physics, we usually assume that, for example, in the canonical ensemble, there is a Boltzmann distribution. Well, the joint distribution of all the variables, or has this kind of distribution is proportional to the e to the power negative beta times e. Well, the e is a energy function contains all the parameters of this distribution. So beta is actually the inverse temperature. If beta is 0, then every configuration, and configuration means this a vector. So every configuration have the equal weight, and if beta goes to infinity, it means that only the configuration with the smallest energy has finite measure. However, given the energy doesn't mean that we can estimate everything about this distribution, because usually it's really difficult to compute the partition function z, the normalization factor of this distribution. So naively, if we want to compute z, we need to do the summation over 2 to the power n non-negative factors, right? So it's not trackable. So for the statistical mechanics problems, we are basically interested in several problems. The first one is how to estimate this free energy. So why free energy? Because z is the summation of lots of non-negative components. It could be very huge. For example, this could be in scale of 2 to the power 100. You cannot even store it. So we would rather store the log value of z, which is basically the free energy. If we can, people in physics are interested in free energy because it gives us the estimate on the phases and phase transitions and so on. And in machine learning, the free energy is basically the log of the total marginal likelihood. So in the machine learning field, the free energy basically tells us how well your model represents your data. In some cases, when you are not interested in free energy, and people usually interested in some statistics of this Boltzmann distribution, such as moments, and representing magnetizations and correlations and so on. And those statistics are usually obtained using unbiased samples, for example, from some MCMC metropolis. Unfortunately, these problems are all belong to the class of p-space problem in the computational complexity theory. It means that it's hopeless to find exact algorithms to solve these problems in general. So, if we really want exact solutions, we usually need exponential algorithms. Otherwise, we have to go to approximation algorithms. So why we care about these statistical mechanics problems? Of course, in physics, it's one of the most fundamental things. And in the world out of physics, it also has many applications. For example, for the combinatorial optimization problems, it is equivalent to finding a ground state of a spin glass system. So it's a ground state of a statistical mechanics problem. And so in this mapping, the energy function of the statistical mechanics problems is nothing but some cost function of combinatorial optimization problems. And by choosing a temperature and set it to 0, with this beta goes to infinite limit, we would able to select some solutions which has the minimum cost function. Okay? So this is how people in the graphic models usually do. In the machine learning field, there are many basic models, such as the Hopfield model and Boltzmann machines, are actually at least inspired by statistical mechanics. Particularly in the Boltzmann machines, people usually assume that the given data were generated by a Boltzmann distribution, which is parameterized by some coupling parameters. Then the learning of the Boltzmann machine is nothing but trying to find the coupling parameters of the Boltzmann distribution. Okay, in the statistical inference, so if we really want to do Bayesian inference, then the posterior distribution naturally translates to a Boltzmann distribution. So solving the posterior distribution has exactly the same complexity as solving the Boltzmann distribution. If we really want to, if we don't want to do Bayesian inference, but something like maximum a posterior inference, then the problem goes back to the combinatorial optimization problems. Well, people want to find most likely configuration, the ground state energy of the statistical mechanics problem. And the last one I want to mention is the quantum computation. So consider a quantum circuit. If we want to estimate some amplitudes of the chosen basis vectors of the final states in the computational basis, then this problem is basically a statistical mechanics problem with complex interactions. I will talk about this later. So here I actually represent my research journey on these statistical mechanics problems. So some time ago, the method I was interested in was belong to some people were called mean field methods. This include belief propagation, survey propagation. There are message passing algorithms, and but they also belong to the mean field framework. The mean field methods are one kind of variational methods. So in the mean field methods, we see that the Boltzmann distribution is really difficult to deal with. So why not just choose a simple distribution? We call it variational distribution, which is parameterized using some parameters. Then we can tune the parameters in such a way that the variational distribution can go closer and closer to the Boltzmann distribution. So by closer and closer, we need the estimate of the distance. People usually use KL divergence as a common choice, and this leads to the minimization of the variational free energy, which is the free energy of the variational distribution. And this is nothing but mean field method and message passing algorithms. By choosing different kinds of variational distributions, we have different kinds of mean field method and message passing algorithms, such as naive mean field or variational mean field methods, beta approximation or belief propagation, or Solid-Stanton Palmer equations, and survey propagation. This is with some specific replica symmetry breaking onsets. And so about in 2019, we began to realize that if we really want to solve particular instances in the real world, the mean field method is not so good. So the reason behind it is that the variational distribution used, the classic variational distributions people usually employ is usually not very strong. It contains not many parameters. So usually we say that the representation power of the variational mean field method is not strong. So why not choose a stronger variational distribution? For example, parameterized linear networks. Yes, we can do this actually. So in about 2019, we started to use neural networks to help the mean field methods and variational message passing algorithms to do the variational mean field, variational free energy minimization tasks via something we call actually the reinforcement learning, basically. And it is really good. It is really good. In some small instances, it works really much better than the mean field method with some common chosen variational distributions. However, in last year also, it turned out to us that the neural networks is not the most powerful thing. If we just give up the variational framework, by the variational framework, I actually mean that we have to choose a variational distribution which gives a upper bound of the free energy. So the variational framework relies on this upper bound of free energy. So given that, we can minimize the free energy. If we just give up this framework, and we have we have more space to do some calculation of the partition function and the free energies. For example, using some techniques borrowed from quantum many-body physics, and this is tensor networks, and this is what I'm going to introduce in this talk. So why is this? Why these problems can have such interactions? Because in my opinion, they are quite similar actually. For the statistical mechanics problems, we are dealing with such Boltzmann distribution. Well, the space for this distribution is about 10 to the power n. N is the number of spins or number of discrete variables. So if we can really deal with such large space, then what we really need to do is some linear computations. For example, if we really want to compute z, the partition function, then it can be turned out to be a inner product of a giant tensor with the all-one tensor. We'll talk about this later. And in the middle, for the machine learning problems, actually we also need to deal with a really large space, the data space. Take this MNIST dataset as an example. Here we have many images, handwritten images. Each image is composed of 28 by 28 pixels, totally 784 pixels. So by answering any machine learning problems, we actually need to deal with a large space composed of all the pixels. The size is about 2 to the power 784. So we call it pixel space. So you may ask that, and you have seen lots of studies on machine learning studies on the supervised and unsupervised field that do not deal with such a large space. So notice that in that case, when you do not use such a large space, you have to use nonlinear functions to transform your working space to a large space. Sometimes you do not know how large your working space, the space you transform to is how large is it. But if you can really deal with such a basic 2 to the power 784 large space, then you do not need any nonlinear operations. So in this case, the tensor network can be very useful. So on the right hand side, there is a control of the quantum state sense. We need to deal with the Hilbert space, and we know that the space size is 2 to the power n. So they actually share the same feature. So we need to deal with such an exponentially large space. So we need effective models, and hopefully, if we can directly work on this large space, we only need linear models. So in this case, the tensor networks could work as a bridge. This is my hope. Okay, so talking about tensor networks, so I put some diagram notations here by drawing a cycle. It means a scalar. One scalar. It could be a complex number or a real number. If there is an edge associated with this cycle, it means that this tensor has an index, and it's nothing but a vector. And if there are two indices associated with this cycle, it means there are two indices, so it's a matrix, and so on and so forth. So the most important operations we put on this tensor diagram is by joining two legs together. So this is a contraction operation. I will give some examples. I assume that everyone has seen this Einstein notation. So on the left-hand side, I have C equals to Einstein AB JJ, means that I'm doing this in the product of two vectors A and B by summing over the common index J. In the tensor diagram, it is drawn simply by joining two open indices of A and B, join them together, and this gives a scalar C, which has no open legs. All right. So another example, C equals to Einstein AB ijjk to ik. This means that we are summing over common index J of two matrices A and B. Basically, it's nothing but matrix multiplications. A times B equals to C, which has two open indices, is the matrix. So a little bit more complex. So instead of summing over one index, so we now sum over two indices of matrices A and B. It means we are doing trace of A times B. This gives a scalar because there's no open index left. Okay, and so basically the same if we sum over indices of A and B between A and B and the common index K between B and C. This gives another matrix D because the number of open indices of A, B, and C is 2. All right. So after drawing this diagram, we can immediately figure out what is the space complexity and the time complexity of these contraction operations. So in physics, basically people use, especially in the quantum many-body physics, people usually use tensor networks as variational onsets for wave functions. For one-dimensional systems, people usually use the matrix product states, which is in the line. And for two-dimensional quantum systems, people tend to use the so-called the PEPs, the projected entanglement pair states. So it's basically a tensor network located on two-dimensional space. And sometimes people also use the tree tensor networks and the mirror, which is composed of small loops and global tree-like structures. And if we want to use the tensor networks out of the quantum many-body physics, for example, in the statistical mechanics problems, we will encounter tensor networks with some different connectivities, maybe with arbitrary connectivities. For example, if we are dealing with the two-dimensional ISO model, then the tensor network we encounter is the two-dimensional one. If we want to deal with some statistical models on sparse graphs or on random graphs, the resulting tensor network would have the similar features. The most terrifying thing is this fully connected one. For example, the Sherrington-Kirkpatrick models, and we have to deal with the fully connected one, fully connected tensor networks. Maybe we do not want to use tensor network in this kind of sense, right? So given this given this I would first introduce how to compute the partition function using tensor network contractions. Let's go back to this statistical mechanics problems. Given a configuration S composed of n binary variables, let's assume that it's on a graph, for example, 2D graph. And so the Boltzmann distribution is written here. So I wrote it as 1 over z times p tilde. So the p tilde is the unnormalized distribution. So I will refer it in this way. So it's basically 1 over z times this e to the power beta e to the s. So the first observation would be that so PS is nothing but a giant tensor. So why I say this? Because PS has 2 to the power n component, right? If we fill every component, we will result to a scalar. So PS is nothing but a giant tensor with dimension 2 to the power n. You can regard it as a vector, or regard it as a tensor, or regard it as a tensor network with any kind of shape you can make. And it's the same as p tilde. The difference is that the p tilde is not normalized. So if we want to compute the normalization of the P tilde, we only need to compute the L1 norm of the P tilde. So how to do this? How to compute this L1 norm? And so basically we need to compute the inner product of the P tilde with a giant O1 vector. Fortunately, we can use the topology of the system and just factorize this giant O1 vector into a tensor product of many small 1-1 vectors. Okay, and in such a way that we can convert the computation of the Z as a contraction of the tensor networks with a specific structure. So let me give a very trivial example. Consider on the left-hand side, there is a statistical mechanics problems composed of two spins, I and J, with interactions encoded in a matrix A. Then it's trivial to see that the P tilde associated with this problem is nothing but a matrix A, but it's not normalized. If we want a normalization of this P tilde, then we just need to sum over all the possible elements of Aij, right? And we see that the components of Aij are non-negative because it's a statistical mechanics problem. And okay, so by doing this, we can factorize the 1-1-1-1 vector into 1-1 O times 1-1. If we put them on two open indices of A, we can do this computation shown on the right-hand side. Okay, using this technique, we can basically compute any partition function of the statistical mechanics problems at a given beta. So why at a given beta? Because we really need the precise elements of the tensor elements of each interactions. Okay. So this is basically the strategy. However, you will see that they have the computation would be exponential algorithm if we really want an exact algorithm. If we do not want the exact algorithm, or if the system is large enough, we may prefer to do some approximations. And another thing is that can we do this computation at beta goes to infinity limit? That is towards this t goes to 0 limit. Because in that case, we would be interested in ground states or the optimal solutions for combinatorial optimization problems. These problems is similar to finding the lowest place in a very complex landscape, and it belongs to the class of NP. So this problem is difficult because some trivial algorithm, some search algorithm will always stuck in some local minimums instead of global minimums. So if we want to overcome those local minimums, basically people prefer to usually do some annealing scheme, either the simulated annealing, which uses thermal fluctuations to cross the valleys, or use the quantum tuning to go away from this local minimum. In particular, the D-Wave company has been studying a set of specific optimization problems on this chimeral graph drawn on the right-hand side, and they actually build a machine to do this quantum annealing for the spin glasses, the ground state problem of the spin glasses on the chimeral graph. So we can actually use tensor networks to deal with this t goes to 0 limit directly. So remember that we have been talking about the linearity of the tensor networks. So all the operations in the tensor networks is linear. For example, the inner product. By defining the inner product, we have the linear space, and there are basically two kinds of basic operations for this linear operations. This is product and plus. So if we replace these two operations by another two basic operations, we would go to this so-called tropical tensor network, or tensor networks with the so-called tropical algebra. So in this tropical algebra, all the product operators were replaced by this plus operator, and the plus operator in ordinary algebra was replaced by this mean operations. So, and we have infinite samples in the system, so it's defined on the semi-ring. So why we call it tropical algebra? Because this name was given by French mathematicians. So there was a Brazilian mathematician working in Paris who invented this algebra. So so the French mathematicians began to give a new name to this algebra. Then they were thinking about how about the Brazil, and feel that Brazil is a really hot place. So why not call it tropical algebra? That's why this tropical algebra comes from. All right. So why this corresponds to the computation of the zero goes to t goes to zero limit of the free energy. Let's give an example. So consider this a computation of F0 and zero temperature limit of this free energy, and we will involve such kind of computations, which involves beta goes to infinity limit and 1 over beta times log something, and unfortunately, this computation will cancel out the beta samples, which is infinity actually, and results to this tropical algebra. So basically, using tensor networks and the tropical algebra, we can compute the ground state energy directly by contracting the tropical tensor network, and find out where are the ground state configurations if we do the backpropagations using gradients actually. Moreover, if we could mix the tropical algebra and the ordinary algebra, so it's something like tropical complex numbers, and we could compute both the ground state energy and the ground state entropy, which is ground state degeneracies. All right, so let's go back to this D-wave machines. On the D-wave machines, there is a chimeral graph. So D-wave machines can solve different kinds of combinatorial optimization problems and the ground states of spin glass problems defined on these chimeral graphs. So now the D-wave machine has 1024 spins, but some time ago it contains only 250 spins, if I remember correctly. And equipped with our tensor network techniques and the tropical algebra, we actually can work out the exact values of the ground state energy and the ground state entropy for the spin glass problems and combinatorial optimization problems defined on the chimeral graphs up to 512 spins using just one GPU. So why is 521 spins? Because now we have the limit of the GPU memory, which is 32 gigabytes. Okay, so comparing with some state-of-the-art method. So the state-of-the-art methods in the applied mathematics in the combinatorial optimization problems is so-called branch and bound and branch and cut algorithms. And so comparing with this method, we see that in some cases branch and bound and branch and bound are much faster and works for much larger systems than us. For example, on the two-dimensional spin glass problems with Gaussian couplings, and two-dimensional spin glass problems with plus minus J problems, it works really well because in these cases, the branch and bound method has a really good bounding method where linear programming. However, it's not. If we switch to some more difficult problems, for example, the spin glass problems on 3-dimensional or Potts model on 2D or 3D, we immediately find that the linear programming cannot provide a really good bound. In that case, our algorithm works better in the sense that it works to a larger system in obtaining exact ground state energy and ground state entropy. Okay, so what I have introduced are exact algorithms So it has to be exponential in solving general problems, especially with an arbitrary topology. If the graphs becomes larger, a little bit larger, the computation resources, the exact contractions cost would be increased exponentially. So if the system is large enough, we cannot use exact computations. We have to find some approximate contraction methods for arbitrary tensor networks. So for finding approximate contraction methods for arbitrary tensor networks, and actually have lots of challenges. The first one is that we will inevitably meet a very huge immediate tensors because of the exponential space complexity. The space complexity must be exponential to the tree width of the given graph. The second one is that we have to do approximations, and we really want the approximations to be global in the sense that we want to decrease the error we made on the final z values, not on the local operations. The third one would be scalability. So in this work, we propose to solve these challenges using matrix product states. First of all, we propose to compress every tensor that we encountered during the contraction process using the matrix product states. And secondly, one is that when applying approximations, we use DMRG basically in the scope of the whole MPS. So the approximation is in the scope of the whole MPS rather than local tensors. So it should work better than just do some local approximations. About the scalability, and since we are using MPS, we can always use a very small bound dimension because every tensor we encountered in this matrix product states are three-way tensors. So if the bound dimension is small enough, we can make it scalable. Maybe this is in the trade-off the accuracy, but we can always make it work for large systems. And this results to an algorithm we call CATN. CATN stands for contracting arbitrary tensor networks. I will give an example to show how it works. Suppose we want to contract a tensor network composed of 5 tensors, each of which is a 4-way tensor. And we say that there's no open indices associated with tensors. So by contracting this tensor network, that is summing over all the common indices and contracting all the edges, we will have a scalar. If the problem associated with this tensor network is a statistical mechanics, then the scalar would mean the position function. And if the problem is the quantum circuit simulation, then the final result would be an amplitude of given basis vector of the computation in a computational basis. All right, so let's start. So first of all, as I've introduced, I will convert every tensor that encountered to a 3-way tensor or to a matrix product state. So here, every tensor in different colors was converted to a matrix product state with the same color. So for example, the red 4-way tensor is converted to a red matrix product states composed of 4 tensors. So for the statistical mechanics problem, the first step is exact because we know there is the standard canonical polyadic decomposition to matrix product states conversions. So after that, we may need some approximations. So after the conversion, we need to do contractions to sum over indices shared by those MPSs. And during this process, we need to keep the matrix product states in the so-called canonical form. That means that so except just one tensor, 3-way tensor, all the other tensors of the matrix product states are isometries. They are orthogonal tensors. In this way, the approximation we made are in the scope of the whole MPS. So during the contraction process, the matrix product states would grow longer and longer, and the scope of the approximation would grow more and more global. All right. So by doing this contraction and approximation is nothing but the DMRG process. repeatedly, we will finally arrive at a scalar, which is a contraction result. Okay, so let me show some results. So here we compare the result of computing free energies of spin glasses on different topologies, on 2D lattice, on regular random graphs, on small world networks, and on the Sherrington-Kirkpatrick model, which is the auto interaction systems. And in these systems, we see that we have chosen the system size in such a way that exact computation of the free energy is feasible in a reasonable time, so we can always compare with the exact values. So of course, our method is much faster than exact computation of the exact results. So we compared with different methods. This include NMF, stands for naive mean field, TAP, the Solas-Anderson Palmer equations, BIT is the beta approximation and the belief propagations. The VAN stands for the variational autoregression networks, which is a neural network-based variational method, which was considered to be really powerful. And the convolutional VAN is the convolutional variational autoregression network. So basically, what we can say that compared with the mean field and the neural network-based variational method, the tensor network contraction method is much more accurate. But we have to note that the tensor network contraction method is not variational. So the free energy computed is not upper bound anymore. And we can choose a different bound dimension such that the accuracy as well as the computational time can be tuned. So we can see that the computation time is about several seconds, which is quite fast. At least it's much faster than the neural network-based method, which is really slow. All right. So let me turn to the third part. Now, if we could make assumption that the interaction matrices connecting two variables in the statistical mechanics problem is no longer real, we could take complex numbers, then this problem would be very similar to the quantum circuit simulation problems. Well, given this initial state and final state, we want to estimate an amplitude of specific basis vector of in the final states. Okay, so why we can do this? Because all so the initial states, the final states, as well as the 1 qubit and 2 qubit gates can be converted as the tensors, right? For the gates, they are 2 by 2 or 4 by 4 matrices. And there are basically two kinds of methods for doing this. The first one is to store the full state vector to track the evolution of the quantum state, and people call it full amplitude. In this method, for this method, one need to pay an exponential space to store this full state vector, so it doesn't work for a very large number of qubits. We can also do some approximation on it. For example, the shooting Feynman algorithm, or use the matrix product states to approximately store this state vector. Another kind of method is to say that we do not store all the possible amplitudes in the final states. We just compute one amplitude at once. So this is known as single amplitude computation method. You can use PEPS method. You can use PEPS-based method, which is a classic one studied in the quantum many-body physics. And recently there are some more advanced methods I will introduce later. And so the first attempt we try to do is to use the CATA to do this approximately. Unfortunately, we found that this doesn't work because we found that the random circuits are really sensitive to the errors we made on the Schmidt decomposition and singular value decompositions. So we turn to the conclusion that we really need to do exact amplitude computations, perhaps with some sampling to obtain to really finish this simulation task. So our task is Google's Sycamore circuit. which is composed of 53 qubits. Google took 20 cycles of unitary operations on it and sampled 1 million samples within 200 seconds, obtained a measure of the fidelity that people call linear cross entropy fidelity, XEB, because they are 0.002. And people say that, and Google said that if you really want to do this classically using for example shielding Feynman algorithm, then it takes 10,000 years using the Summit supercomputer. So Google said that, well, this task is not trackable on the classical computers. So this actually attracted lots of interest. Just after Google, IBM claimed that if one could use not only the memories but also all the hard disks of the Summit, totally 250 petabytes, then one would be able to store the 2 to the power 53, the stat vector. Then all the computation can be finished in 2.5 days. But we know that it's not possible to use all the disk or the hard disks of Summit. Right? In 2020, in about March 2020, Gray and Kutis proposed the Cotangra, which introduced a very advanced a method for finding a contraction order of the algorithm. This reduces the computation time for a single amplitude using a single GPU to about 3,000 years. And later on, Huang et al. In Alibaba's group, computational group, invented another method, which is also based on finding a very good contraction order, plus some other techniques such as slicing technique and reject sampling, and claim that using more than 20,000 GPUs, basically the supercomputer of Summit, this task of sampling 1 billion samples can be done within 20 days, given almost the same XEB value as Google's. So let me introduce our method. Our method is in line with Cotangra and Ali's method. It's the tensor network contraction method. So by compute just one bit-stream amplitudes, we need to contract the whole tensor network. And in the case of the Google's Sycamore circuit, the tensor network is in a 3-dimensional space. It looks like this. So on the left-hand side, there's an initial state, and on the right-hand side is a final state. And if we pin the final state by choosing a basis vector, then the amplitude can be computed by contracting the overall 3-dimensional tensor network, which is really difficult to compute. So our idea here is to compute a large number of correlated bit strings at once. So the basic idea here is to find the central. Actually, the central idea here is to find a cut state denoted by this yellow plan to separate the whole tensor network into 2 parts. So the big part and the smaller part. So the big part we call it big head, and the smaller part we call it the tail. And there are some edges connecting the head and the tail. So the trick here is that we only need to compute or to contract the big head network just once, and reuse the result for computing all the possible bit strings in the tail tensor network. Okay. So in other words, the red cycles on the right hand side are not pinned, so they are open indices. So this relies on finding a very good cut separating the whole 3D tensor network into 2 parts, into head and tail. And the cut must satisfy several constraints. The first one is that by choosing this cut, this head tensor network, it must be able to be computed in a reasonable time. The second constraint is that it cannot have too many connections connecting the head and tail. So the edges connecting head and tail must be as few as possible. The third constraint is that the tail networks must contain as many as possible the open qubits in the final states. Okay, so using the algorithm, we find a cut that basically satisfy all the constraints, and which is showing on the right-hand side. So this is
Can I ask a question? Can you go back to the slides?
Yes.
Previously, can you repeat what's the definition of head tail? Like, is it the blue part is the head and red part is the tail?
No. Can you see this yellow cut? It cut a corner from this from the overall tensor network.
Okay.
So the corner that has been cut by this by the plan, the yellow plan, is the small part. It contains lots of red qubits that is kept open.
Okay.
While the left part, the big one that in behind this corner is the head. So
so like this is a 2D circuit and time dimension, and you think of this as a 3D.
It's a 3D. It's a 3D. Because
and then you cut a corner for like
The overall computation of one amplitude is a 3D tensor network because the layout of the Sycamore circuit is on 2D. So the third dimension is nothing but you can think of it as the time and the dimension of time by applying operations. All right. So having a look at the complexity, so for Google's complexity is really huge. So we don't have some precise values. For Contangra, the complexity for computing one bit string is about 10 to the power 22. For Alibaba's method, computing 64 bit string amplitudes, the complexity is about 10 to the power 18. For our method, the complexity of computing 2 million bit strings is basically the same as Alibaba's method for computing 64 bit string amplitudes. So this enables us to really do this computation. So we actually finished these experiments using 60 GPUs in 5 days. So and obtained some 2 million bit string amplitudes and probabilities. Here I plot the histogram of the probabilities of the obtained 2 million bit strings on the left panel, and we can you can see that it's close to the expectations, which is the red line. The red line denotes this Porter-Thomas distribution. And if you consider the totally 2 to the power 21, 2 million bit string probabilities, and the XEB value is 0. So why is 0? Actually, it is expected because the XEB can be treated as a measure of the accuracy or distance between two distributions, your generation distribution and the real Porter-Thomas distribution. Okay, so here we have enumerated 2 to the power 21 bit string entries. This means that our generation probability is actually uniform. So the XEB between uniform distribution and the must be 0 by definition. So if we use all the 2 to the power 21, the 2 million bit string probabilities, the XEB must be 0. Fortunately, since we use classic computations, we have all the values of the probabilities. So we can select some bit strings out from the uniform distribution to make the generation distribution away from the distribution. And we can make the closer and closer to the true distribution in the sense that the XEB is larger. Maybe not very close, but not in the sense of close, but in the sense that the XEB is increasing. Okay, so on the right-hand side, we see that if we can select some of the bit strings, we can increase the XEB. By using 2 to the 100% of the bit strings, the XEB is 0. By using 80%, the XEB is about 0.2. Also, by using only 10% of the bit strings, the XEB could be larger than 2. So finally, we chose half of them, 1 million bit strings. This gives XEB equals to 0.739. Okay, we have similar results for the circuit with 14 cycles, and we can do some experiments. We also have some results on the conditional probabilities, which is difficult for quantum circuits to do, but due to time limit, I'm going to skip this. So let me go to the discussions. So basically, since we have the classic computation of the probabilities, so it has some advantages as long as you can do this computation. So first of all, the amplitude is exact, so this allows you to poster select something, and the fidelity is higher because we can do important sampling to select some bit strings to make the generation distribution away from the uniform distribution. Okay, and the third one is that since we have this all the probabilities and conditional probability, we can do something more interesting that which is hard for quantum hardwares. And we also have some disadvantages. The most significant one is that the algorithm is exponential. It has to be exponential in obtaining exact amplitudes. But because this problem is the BQP problem, so Google's hardware is guaranteed to finish it in polynomial time. In this sense, if Google could increase the number of qubits or increase the number of cycles by 2 or so, then the computational cost we would pay maybe would be 4 times or 8 times larger, which is maybe not affordable anymore. And another one is that notice that we have computed 2 million correlated bit strings with. But the Google samples are not correlated. Okay, this is another significant difference. The last point is that we obtained a large XDB, but doesn't mean that we have already obtained a distribution that is closer to the true distribution, or we have a higher fidelity. It may be not, because if one could choose another measure for the fidelity, and it's not clear to us which one could be higher. All right, so I think I should stop here, leaving some space, some time for questions.
Thanks for the great talk. I want to ask a bit more about the Google simulation.
Sure.
So can you like maybe explain the idea that you get a more efficient method, like you design this cut and design this head and tail.
Right.
So what's new, like that people haven't used before that?
Right. So what's new here is to use this cut to compute a large amount of bit strings using just one single contraction. So the most computational effort was put on contracting the head, the big head tensor network.
Okay.
So so once we computed this big head tensor network, we can reuse the result. The result is a vector. The dimension of the vector is 2 to the power L. L is number of edges connecting the head and the tail.
When you say that you computed the tensor network, you mean you contracted all the head?
I contracted the head, resulting to a vector. It does not result to a scalar, because there are some open indices, open edges connecting the head and the tail. So you see that the number of edges connecting them must be of as few as possible. Otherwise, you cannot even store this contracting results. So we finally find a cut satisfying some constraints. The first constraint is that the number of edges connecting the head and tail is small. The second one is that contraction cost for the whole head tensor network is doable. And the third one is that the number of open qubits in the tail network is as large as possible. We finally got 21.
Good. So is this like depending on the particular random circuit you're working with, or it's more general, you can make it work for?
I think this.
Like if you change
it's
the
quite
circuit.
general for tensor network to have such has such structure. You can always, so people now use partition-based method to find a good contraction order. Why this works? I think because in general, the tensor network, especially on irregular tensor network, has such kind of structure to be explored.
Okay, thank you.